All right, so I'm going to go over here once again and showcase this little presentation over here. So when we come here into Google Colab, you can either open the file, right, by going through your file, or you can upload the file that we give you. The point here is that you can start writing your code. It has pre-installed Python, and what we did up here was install all of these. We installed the libraries for Qiskit. We installed Qiskit, and here's some of the Python libraries that we need. And here are more quantum libraries that we need. It's important for you to understand that in order to create a quantum circuit, this is what we import. In order to be able to represent things with pauli operators, this is what we import over here. This is going to be part of your quiz, so I want you to really understand the libraries and the things that we're doing and why we're doing. Because if you have to create, if we just ask you to create a pauli operator, then you need to know what to pull in. In order to create some of the other visualizations, you'll need this for the histogram and the vectors. And so some of the circuits that you're going to see created are going to be using that. This AER simulator is really critical when we're doing several shots. Over here on the estimator and runtime services, one of the common mistakes that people make is that they only install the Qiskit either 2.0 or 2.x or 1 something, but they forget to install the runtime. These samplers and estimators and all of that, this is what's critical for some of these shots and simulations also. So we have to make sure that you not only install the Qiskit version, but you install the runtime and then import the proper sections as well. Okay, so back to these pauli operators. I'm just monitoring the chat. Everyone was able to install that first part. Okay. So let's go in here and look at these pauli operators. The code is in the Discord channel. I can put it back here. I will be sending the notebook after. This is mostly for the people who have never seen this and don't know how to use Google Colab. All right. So I'm going to open a new notebook that I used for a demo. And share this part with you. Okay. So what's important for you to understand here, let's see what the questions are. Okay, so far we're good on questions. So we're going to go to explaining a little bit about these pauli operators. It's a really silly way to kind of look at it, but if you think about these pauli operators as families, you can think about what they do. The x-axis, in which, you know, the flat line of the horizon that we see just flips its state between 0 and 1. The y state adds a phase and flips between the y state and combination between the matrix products. And then the z states change the qubits phase, which is also what we call it's really important for quantum teleportation because we call it like a negative phase, which is kind of why they have them grumpy over here. And then I is also, I mean, I'm describing it as it does absolutely nothing, but it kind of helps in the combinations of them, and you'll see in the exercise why that is. As you saw, the IBM representation kind of takes you through tensor products and all of this. And what's important for you to understand here is that, for example, in the matrix of X, right, you see that this one's 1. And so you'll be able to see that it is in a point in time. I'm going to show you the composer in a second so you can visualize it 3D within the block sphere. And it swaps the state of this ket for between 0 and 1. So like the coin flip or the typical coin flip, because sometimes we want things to be in one state or the other in order to achieve entanglement. In here, we have the twister between the I just thought it was funny that this is what they called it, but what it does is a 90-degree twist. So it's not necessarily an entire product or of a ket, but it's 90 degrees. Remember that these are operators within angles, which is really important for us to keep in mind. And so if you think about the Y as a 90-degree change, then when you are looking for, if you're going from 180, from 0 to 90 to 180 in the different planes, then you can achieve this with this kind of operator. In the Z one, we're going to thinking as the negative phase flip. What's important here is that you see this -1, that negative phase, which I really enjoy, part of quantum, is that you're going to be able to use this negative phase, or being able to put different circuits into this negative phase will allow you to do things for the basic of quantum teleportation, phase kickback, which is part of Grover's algorithm, and different things, which is just a search and unstructured search algorithm. And so knowing how to add to your circuit, not only changing it from 0 to 1, but changing the angle, which you're measuring, and then adding the negative phase will help us achieve a combination of steps, algorithms, right, that can bring us the circuit that we are creating to an entangled state, to a state where we can send quantum information in this negative phase. There's a lot of good videos on phase kickback that tell you mathematically how you get to this negative phase, and they're quite amazing. I can post one of my favorite ones from someone who helped me believe that I could learn quantum a couple of years ago. And it is, if you are a mathematical person and you love those deductions, then I suggest looking at that video. If you need to understand, if for you at this point, I just need to know the practical applications, and yeah, don't give me the mathematical stuff, which we're trying to give you last, then you just need to know that in order to achieve certain states, it is really important that you know how to encode into the negative phase. Now, I'm going to stop sharing here, and I'm going to go back into the notebook and open up that portion so you could see it resolved. Again, oh, actually, Sue Dickens here. So what I can do is I'm going to send this notebook in the Discord, give you the resolution once we come back. It's super important that you are able to see what the combination of states brings us to for these pauli operators. And while I get Sue Dickens queued up, I would like to show you what is the composer and why I keep talking about it. Okay, so Dickon, if you can get off mute so I can start introducing you shortly. Okay, so this is the composer. I want to show you Z-gate and what it does. So if we have here, so when we're talking about the pauli operators, right, or the gate, this is the pauli operators. You can see here that the probabilities are changing, and now it changes here. If I add an X gate, where is it? We'll get to Hadamard in a second. Then, no, this is not what I want. What do I want? I just want to show you this. Over here is the code. So we're saying that we want a quantum registry here. Let me annotate here. We want this is what we're doing. All we did was apply the Z gate, okay? And then if you look at this in this state, let me take this off so I can look at the angle. So you can see the angle and the state over here. It's kind of really small, but if you come here and then you apply an angle rotation, you'll be able to see how it starts changing the states and the location and the phases. Down here, you'll see that in the x it's 0, pi over 2, pi and pi, 3 pi over 2. And so we're talking about the different phases of the clock. Don't worry if this doesn't make sense. We're going to play with it more with your assignment so you can see how this generates. But if we delete these, you'll be able to see that cut 0, for example, here is probability. It's one probability of a 0 angle and in that state, right? Because this is a 4 qubit state. So you see 1 0, 2 0, 3 zeros, 4 zeros in the state. So we have a probability of 0. Now, if we apply some of these gates here, you'll see how that's going to start changing. So let's apply a Z gate to this. Now we have added a negative phase to it, and then we can continue going until we create a state where we flip it and you start seeing where the angle is. The idea here is that you want to be able to play with this sphere and see it visualized, all of the gates and operators that we bring you to, so you can see them all visualized here. So this is mostly for you to play. Now, I'm going to show you the example of the code resolved after we go through Zidikkin's presentation. We've covered some of the basics, how to open things on Google Collab. You saw the way that they explain the pauli operators. You just need to know in each dimension which one they're trying to flip, what kind of rotation, 90 degree, 0 to 1, and we will get back to this after our presenter. What we're going to do is we're going to continue our quantum machine learning track. Zidikkin, are you ready?
Yes, I'm ready.
Awesome sauce. So let me just do our usual quick little presentation here, and then I will hand it over to you. Where did I open this screen? Here we go. Oh my goodness. And I almost forgot to present Shireen. So let me do this over here. Shireen today is our simultaneous translator, which makes what we are doing possible, right? So let me present my screen here in a different language. Okay. So Shireen is our simultaneous translator. She has over 10 years of experience in corporate finance. She's leading global teams in a matrix environment and simultaneous interpretation. She's developed a strong skill set that combines communication, technical, and financial expertise. She's lived in Mexico, Israel, and the United States, and she brings a diverse cultural perspective to her work, enhancing her ability to navigate complex financial environments and facilitate effective communications across languages. Thank you, Shireen, for your time and expertise in helping this reach more individuals. Now, let me introduce our next speaker. So Zidikkin is going to continue our quantum machine learning track, and he is going to walk us through data encoding. As you know, Zidikkin Pramanik is a research in quantum machine learning, currently pursuing his PhD at CVPR Lab IIT Ropar. His academic background spans an MTech in remote sensing GIS from IIRS, ISRO, where he topped his program in Masters in Physics from JIS University. His work lies in the intersection of quantum computing, geoinformatics, and artificial intelligence, focusing on developing quantum-enhanced algorithms for Earth observation, computer vision, and data analysis. He has been associated with IBM Quantum as a global intern, contributed to QIntern, MEITY projects, and co-organized the Qiskit Fall Fest 2025, along with me and other really cool people and advocates. He's also a recipient of multinational hackathon awards, and his research reflects a continued effort to bridge quantum innovation, real-world geospatial, and computational challenges. So remember, everything he gives you is going to help you get that badge on quantum machine learning. And when he's done, I will show you where that class is, so we know what we're aiming for, where we are going to be headed for next week. And then I'm going to continue walking you through the pauli operators with the code, give you the notebook, et cetera, so you are able to walk through these exercises with us. All right, Sudikan, thank you. Take it away.
Yeah, hello everyone. Ma'am, can you allow me for sharing the screen?
Yes, sir. Huh. Why is it not letting me do this? Go ahead, share your screen.
Yes, thank you so much.
And I'm going to remove the unmuting, and you are good to go.
Yeah, so hello guys. Wish you a good day. And thank you, ma'am, for such a nice introduction. So yeah, last day we studied about data. We studied why do we need a computer. We studied why do we need machine learning. And we also learned the ABCs of machine learning. Now, gradually, after finishing last day, we'll today enter into the area of quantum. So, to get into the area of quantum, we need to know data encoding in quantum machine learning. So, first thing is data encoding, and not only for machine learning, for doing any task in quantum with a real data, you need to go through data encoding. So, what is data encoding? So, see, if you look carefully, there is CC, CQ, QC, and QQ. So first stands for the data type, second stands for the computation. So CC means classical data, classical computation. QQ means quantum data, quantum computation. So what is CQ? Classical data and quantum computation. Researchers are mostly interested in classical data and quantum computation. So I'll be more focusing on that. So classical data is your images, your texts, your videos that you go through every day. Quantum computation is using a quantum computer to work on that data. So I'll have a classical data, I'll use a quantum computer, and I'll work on that data. I hope it is clear to all of you. Okay, now, so to work with encoding, we first need to understand notations. Okay, so here I'll first talk about our data vector X, M sample, N feature, phi for mapping, U for circuit emulation. So these are so many terms. I hope it is a little bit maybe difficult for you. So let me go through it one by one. Okay, so I'll close this presentation. Just wait for 1 second, and I'll jump into yeah. So can you see my screen? Is my screen visible? Yeah, thank you. So suppose I tell you about a data set. So I told, what do I have? I have X data set. Then I have M number of samples, N number of features. So this is my data set. This is my samples. This is my features. Now let us understand it in a very simple way. So let us go and talk about house price prediction. House price prediction. So we can have some important features for that. One feature can be, feature one can be how close it is to the bus stand or how close it is to the railway station. So vicinity can be a factor. Second factor can be what is the size of your house. So size can be a factor. So second feature can be size. First feature can be vicinity. Third feature can be the locality in which you are trying to take the house. So maybe it is closer to the railway station, but it is not at a very proper place. So if you are staying in New York or Tokyo or Mumbai, your house price is going to rise high other than other places which are not that much expensive. So locality is also a feature. So let me take this feature. So these are features. Now, what are samples? So suppose I have seen 3 houses or 4 houses. So here my samples, suppose there be 4 features. I have 3 features, so there are 3. So 4 sample means for sample 1, I have 3 values. So let the first value be 1, second value 2, and the third value -5. Suppose I have given it some numbers. For the house number 2, let that be 4, 7, 8. So that means 8 is the value that I have given it according to the locality. Similarly, x3, x4, let me put some values into it, 0, 1, and 3. And this one be -1, -3, and 6. So you see, we got a set. And if we define this set, we can create a kind of table. This table has n features, m samples. And where, if I just simply copy paste it, you have it here. I hope it is clear to all of you. So we have X is my data set, M is the number of sample, N is the number of features. Okay. Now, if we want to work with data, we need to understand that our variations are not across the horizontal area. These are not our variations. This is not my variation. Because I'll be comparing variation across a feature. I won't be comparing variation across a data. So if I'm looking at the floor area, I'll be comparing the variation across floor area. If I'll be looking at the vicinity, I'll be comparing across this. If I'll be looking at the locality, I'll be comparing across this. So I'll be comparing across the features. This is the most important part that you need to understand before working with the data. Okay, so I'll again go back to my PPT and kindly tell me if it is visible. Is it visible? Yeah, thank you. Okay, now I told here one thing about phi. What is phi? Phi represents my any mapping value of the classical is phi. What is ux? Same thing in quantum. So it can be a mapping in quantum or a computation in quantum. So both of them are doing the same thing. One in the classical area, one in the quantum area, but the function is same. Okay, so first we need to understand that do we need normalization in this and why do we need normalization in this? So do we need normalization? So what is normalization? Suppose I have a actual data. Normalization does is it compresses the data within certain limits. So as you can see that our data was spread out, it compresses the data in certain limits. So let me explain one small thing. So if we look closely here, you see that we are comparing the value with a minimum value, a maximum value minus minimum value. This is known as mean max normalization. And if you're doing the same thing, on the quantum data, that can also be a normalization. In that case, we will just divide it by the value or the inner product of the space. So let us look at the value that we took last time. So we had this value 1, 2, -5, 4, 7, 8. You remember we took this value. Suppose we have 3 features, we took this value, just what we wrote beforehand. And if you normalize, you find out that the value that you have by min max scaling is changed. And the maximum value that you have is 1 and the minimum value is 0. So that is a min max scaling. Similarly, if you distribute it across a mean region, you get a Gaussian standardization. So if you look into it carefully, this was your original data and it went from 8 to -4 to 8 to -2 to 5. So this was the range of your data. And after normalization, your entire data shrunk and came into a range of units. So this was mean max normalization. And if you look here, after standardization, it is almost similar, but a little bit spread out across a diagonal. So if you look at the last diagram, so in a standardization we spread across a mean value, across a z score. In normalization we scale across a mean max value. Okay, can you normalize it, everyone? If you can, just write down the answer. I'll give you only 10 seconds. It's a very easy one. If you can just say the answer. Can you normalize the state psi? Okay, let's see. So see, this is how you normalize it. So what you do is you take the inner product. So when you take the inner product, what you find out is you get the square of 4 square, then 3 square, it comes to 25, and then you divide the state. So it becomes 4 by 5, that is root over 25. Yeah, absolutely, absolutely. That's fantastic. Manthan J. Fantastic. Yeah, that is the answer. Good job. Okay. So yeah, I hope you get it. Yeah, any questions? Okay. Okay. So now, as we have understood what is normalization and we understood why do we need on normalization, we will get into the types of encoding. So encoding can be broadly classified into 3 categories. One category is only based on the basis states, another on the basis of angle, another on the basis of both product and entangled state. So first, we'll slowly cover one by one and be very careful, because if you don't understand encoding, you won't be able to do further in any quantum algorithms. Okay, because first thing is you need to convert the data to a quantum data. So first, on the basis of states, so first we have basis encoding. Okay, so what happens in a basis encoding is it's a quantum encoding method where classical data is represented directly using computational basis state. Now what do I mean by computational basis state? Okay, let us get into a code, and if you can see this code, can you see this code, everyone? Can everyone see this code? Yeah, thank you. So if we go for basis encoding, the thing that we are doing is we are representing each of the numbers by their equivalent bit value. See, 5 is represented by its bit format, 7 by bit format, 0 by bit format. If we represent everything by its bit format and then we add all of them in the order of LSB to MSB, then we get an entire large bit number. And simply we can put that bit number in every qubit as one bit in every qubit. So let me tell you in another way. Suppose 5 can be represented as 101. Now let us represent it by using four bits. So it goes to 0, 1, 0, 1. So first 4 qubits will be 0, then 1, then 0, then 1. So see, it is 0. It is x. X means 0, then x, it turns it to 1. So 0, 1, again 0, again x. That means again 0 turn to 1. So 0, 1, 0, 1. And accordingly, you can plot 7 and 0 and you will get this state. Is it clear? Okay. So I hope it is clear. Similarly, if we plot 4, 8, and 5, and we can say that we will be getting this state. And this is the representation of the quantum circuit for representing 4, 8, and 5 in basis encoding. I hope it is clear. So can you encode the number 5, 9, and 2? If you can, just tell me how many bit length per number are you taking? That is my question. My question is mainly the second part. How many bit length per number are you taking? And if you can encode it in basis, do it. I'll give you only 10 seconds for the last part of the question. First part, okay, you can skip. The last part is important. 16 bits. Okay, let's see. Let's see. Let's see. Yeah. So okay, 8 bits and 16. Okay, let us see what is the answer. Let us see what is the answer. So suppose if you want to convert 5 to its bit value, it will be 101. That's fine. We can encode it using 3. We can encoding 2 using 2. We can encode 9 using 4. But to maintain the order, we need to keep the maximum bit value. So the maximum bit value here is 1, 2, 3, 4. right? So we have to maintain it. That's why you have to give 2 zeros for 1 0 for 5 and 2 zeros for 2. So that brings us to 4 4 4, that is equivalent of 12. So we need total of 12 bit length, and for each representation we need 4 bit values. Okay, so let's go for amplitude encoding. Now we saw in the last case that when we are representing the qubits, representation of one state based on how many number of bit we want to represent it for, it is taking that much number of qubits. Suppose I want to represent a bit in 4-bit length, then for one value it is taking 4 qubits. So for a real life image, suppose I want to work with an image or a data, for a real life data having any number, it is very difficult to have that much number of qubits. Then what will we do? So we have amplitude encoding. So what it does is that it maps the value as an amplitude to any given state. Now, what do I mean by to any given state? So let us explain that again by this code. So let us go to amplitude encoding. Okay. Suppose I have the value 4, 8, 5, and 0. First thing I told, we need to do normalization. So how we will do normalization? We will square root 4 square plus 8 square plus 5 square plus 0. That will be root over 105. Now the target state will be 1 by root 105 of the first value, then second value, third value, fourth value. Okay.
So Dickon, can you
Yeah.
make can you scroll and make it a little bit bigger?
Okay, I'll try.
And just control scroll up with your mouse. There you go. There you go.
Yeah.
Perfect.
Is it clear?
Much better.
it-
Yep. Mm-hmm.
Okay. Thank you. Thank you. So what we will do is that for amplitude encoding, first we need to normalize the data. Then the normalized value will be put into every consecutive states. So if we start from state, see there are 4 values. So 4 values can be plotted in 2 to the power 2, that is less than equals to 4. That means 2 qubit is required. So the qubits that we get from 2, the composition of tensor will be 0 0 0 1 1 0 and 1 1. So first we'll go for 0 0, the second will go for 0 1, third for 1 0, and the fourth for 1 1. This is how we will put these 4 values. If we have 5 values, then we'll put it accordingly, and we need to take 3 qubits for that. Okay. So if we just put these values, it becomes a very complicated circuit, and Qiskit has found out a way to put it directly, and then we will get a circuit like this. This circuit represents exactly these 4 values. Okay. Similarly, if I represent this number of values, 9, 8, 6, 2, 9, and 2, then can you tell me how many number of qubits we need? 1, 2, 3, 4, 5, 6. How many number of qubits we need? Who can tell that? 10 seconds again. How many number of qubits we need? How many number of qubits? 24. Okay. Anyone else? I appreciate you are trying. Thank you. Anyone else? Okay. So we need to have number of qubits, which is n, for the value less than 2 to the power n. It feels a little bit complex. Let us simplify it. So it is 1, 2, 3, 4, 5, 6, right? Okay. 6 is greater than 4. So we cannot take 2 to the power 2. That means 2 qubit is not sufficient. 6 is less than 8. That means we can work with 2 to the power 3. So how many number of qubits we need? Only 3 qubits. Okay. So this will be put in 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, then 1, 0, 1. Okay. So let us look into it. See, we have 3 qubits and we have put our values accordingly. I hope it is clear. So we can put any number of values, but the circuit will be very complicated, very difficult to explain. But see, how many data do we have here? If we look 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 means 15 is less than 16. 16 represents 2 to the power 4. So how many qubits it will accommodate? 4 qubits will accommodate this entire value. Okay. So therefore we require only 1, 2, 3, 4 qubits. I hope it is clear now. And accordingly, we can create much more circuits. Okay. So having said that, I hope you got some idea about amplitude encoding. Now, can you answer this question? How many qubits you will need to encode 10213? First, okay, 2, okay, anyone else? Try. It's very good that you are trying. All of you try. I'm there to help you out. See, our objective from EnLuz is to take you more towards the IBM certifications. Okay, so these things are essential because they'll give you only 2 tries. And out of 20, you need to score 16 in those 2 tries to clear it. You copy them, give them to ChatGPT, you won't get the answers directly. So forget that. You need to understand the things, then you need to work. Okay, otherwise you won't be getting the certificates. 2, 3, 3, 2. Okay. Okay. Okay, so let us see. So how many values we have? 5. So that is less than 8. That means less than 2 to the power 3. So how many number of qubits we need? 3 qubits. Okay, what is the target vector? We square it, sum it, square root it. That gives us 15. The vector divided by 15 is my target vector. And how do we put that in the target state? Sequentially. So 0, 0, 0, but we had one 0 here. So we are skipping 0, 0, 1 for that. Then we put 2, that is 0, 1, 0, 3, and accordingly. I hope it is clear. Okay, so we understood how we work using the basis states. Now, all of these have some drawbacks. So if we look at basis encoding, that requires a lot of qubit. If we look at amplitude encoding, it is very difficult to put the values accordingly and work with them when you try to fetch the data. So amplitude encoding is taking less number of qubits, but it is difficult to work with it. Okay. Now based on angle. So based on angle, we have angle encoding, phase encoding, and dense encoding. First, we will go into angle encoding. If you look carefully, see, we have 3 kinds of gate, Rx, Ry, and Rz. But in angle encoding, we can use only 2 kinds of gate, that is Rx and Ry. That is, we need a rotation about X or Y. Now, as ma'am showed you in the last class, that X and Y are these 2 axes. So when you are rotating about them, you can see that the qubit is falling from top towards the bottom or from bottom towards the top it is going, right? It is not moving horizontally across the body, okay, across the equator or across any, you can say, latitude. It is not moving. It is moving across a longitude. You can think of it in this way. So this is the Rx theta. This is a gate. This is the Rx gate. This is the Ry gate. So we will be mostly using Rx and Ry gate. Now, let me show you a little bit of code implementation. So this is the angle encoding. If you look carefully, I am encoding a value. Okay, is it clear now? Is it visible? Okay, I'm encoding a value of pi by 2. And when I'm encoding a value, see, it looks like this. So pi by 2, if you convert it, you are going to get this value, and you are encoding this value in both of these states. Okay. Again, if you look at this on the Bloch sphere, and you are rotating it by pi by 2, you can see that it is falling from top by an angle of pi by 2. See, it's all by the code. It's all by the code. So it's not done by doing editing in Photoshop. This code is doing the entire thing. And I'll share the notebook file. You can try it at home also. So it is happening in this way. So suppose you want to plot any number of states by the number of deviations that you need, how many small angles that you want to create. You may not go directly by pi by 2. These small dots represent every small divisions I have made for the angle. So it is not that you have to always move by pi by 2. You may move by any number of angle, any small amount of angle that you wish to do. Okay. So this is your angle encoding. And suppose here we are encoding pi by 4 and pi by 4. So it will be a similar circuit with pi by 4 encoded over there. Okay. So I hope you got some idea about angle encoding. Now, can you answer this question? Can you encode 2 short prices via angle encoding? Can you encode this data 1000 and 500? Can anyone say what will be the problem if we directly put these values 1000 and 500 into that and try to encode? What will be the problem? Can anyone tell me? Yeah, I'll give you 10 seconds. Try. You can always be right, you can always be wrong, but unless you try, you won't learn. Okay, see, multiplying by 1000 or multiplying by 500 will create a problem. Let me tell you, we won't be sharing the chat. Yeah, absolutely. It's a learning space. We are helping you to get the certificate. Don't worry. Okay. So if you look one thing, the maximum angle that we can get is 2 pi, right? So just imagine you are putting the value 1000, qubit size is more. No, that is not the problem. Let me tell you what the problem is. So 1500, if we put directly, it will do a complete rotation. Okay. So because we have to scale it in order of pi by 2, so it will do a complete rotation. So every multiplied by even number, it will do a complete rotation. So 1000 is 500 times 2. That means giving this and giving 500, that is 250 times 2, won't lead to any meaningful outcome. So what do we need to do to get a meaningful outcome is, as we told, we need to do a normalization. So first thing, for any data like this, you need to normalize across the feature. So when you normalize, you find out that for a min max scaling, this value scales to 1, this value scales to 0, and what you do, and then you put this value multiplied by 2 pi and you put it here. Always remember, whenever you are trying to put a value into a gate, into RY, RX or RZ gate, always try to make the maximum value equivalent to 2 pi so that you can unleash the maximum potential of it. Okay. Okay. Now, as we have understood angle encoding, let us get into phase encoding. So what is the difference here? See, in angle encoding, we told that we are changing the theta, but in phase encoding, we are telling we are changing the phi. What is phi? If you look carefully, in angle encoding, we are moving from the top to bottom, but in phase encoding, we are moving along the equator, right? Along the latitude. We are moving along the latitude, not along the longitude. That means we are changing the azimuth, what we call it as azimuth. We're changing the azimuth, okay? And this is a phase gate representation. And phase gate applied over 0 remains 0. Phase gate applied over 1 gives e to the power I of that value. So let me show you a code implementation of it. So this is your phase encoding. So how you are doing phase encoding is, you can put a header mode, not put a header mode, that's not a big issue. You are getting a phase gate. So this is a phase gate. If you can see, it is written by P. You are putting a phase gate, and I'm changing the value by pi by 2. So it's simple. So if I'm changing the value by pi by 2, it will rotate from here to here. And in this case, what I'm doing is I'm dividing it into a multiple number of times. So it is showing multiple number of dots. So I'm changing it slowly by small angles. Okay. 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 So we understood what is phase encoding. Okay. Now, suppose you have this value. You want to put this value as a encoding. So how many number of qubits you are going to need? See, in one line, what we can do, we can put a maximum of one value. So if we have 10 values, we will require 10 qubits for that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For 12 values, we need 12 qubits. So 0 to 11, these are 12 qubits. I hope it is clear. So this is your phase encoding. Okay. So previously we encoded in phase, and we can also encode in RZ gate. So instead of phase gate, we can encode in RZ gate. Both of them are doing the same thing, almost closely, but not exactly. And if we plot, we can observe it in this way. Okay. Now, can you answer this question? What angle shall we scale the phase encoding? By pi by 2, by pi by 4, by 2 pi. Yes, Senthil Kumar, you are absolutely right. We need to do min-max scaling. Thank you. Yeah, for this answer, anyone? Pi by 4, okay. Anyone else? Anyone else? By what scale? By what scale do we need to put an angle? Yeah, Mansidago, you're absolutely right. Absolutely. Yeah, we shall go try. Yeah, we need to scale by pi by 2. By 2 pi, sorry. We need to scale by 2 pi. I hope it is clear. Not pi by 2, by 2 pi. Because the entire angle length is 2 pi. So we need to put it by scaling it to 2 pi. Okay. Okay, now we come into dense encoding. Now, and why this is important. So we had angle encoding, we had phase encoding. One changing by Ry and Rz, another changing by Ry or Rx, another changing by Rz. Now the scientists thought, how about we do both? We change the angles also, the thetas also, and we change the phases also, the phi's also. So they introduced another method that is known as dense encoding. Now this is very important. So in dense encoding, you can encode at max 2, not more than that. That means if you put a RY, then you can put a RZ. If you put a RX, then you can put a RZ. But you cannot put a RY, RX, RZ. That will turn it into another form of encoding, but that won't be a dense encoding. Okay. So in this case, we are doing rotation both about X or Y and Z. So let us look into dense encoding. So this is our dense encoding. Now, if you look carefully, you see I'm putting here a RY gate, right? And simultaneously after that, I have put a RZ gate and I've put the values 3 and 7. And if you look carefully, see how it has changed. So it is not at the bottom, it is not at the top, it is somewhere on a latitude in between. So it has changed by theta and it has changed by phi, and its final position is somewhere here, if you can see. So it is not on this line, it is not on this line, it is somewhere in between at some position. So these are very interesting thing. So if you are doing only angle encoding, we are varying across either Rx or Ry. Okay. Now, if you are using only phase encoding, we are varying across Rz. But if you're using dense encoding, we are varying across the entire Bloch-sphere surface, and this is very important. Okay, so by only using these 3 gates, somehow you are able to move around over the entire Bloch-sphere. Okay, so let us again come back. So this was your dense encoding. Now, how many qubits will be required to represent the data below? Can you tell? 10 seconds. It's very easy. Remember, how many values can each qubit encode in dense encoding? That is very important. If you know that, this is a very easy answer. Yes, Senthil Kumar. Absolutely right, you are. 7. Okay, Mansi Raghav says 7. Anyone else? Anyone else? 4. Okay, Vishal says 4. Okay, anyone else? Okay. No, as we said, okay, Fabian 3. Okay, let's see. Okay, Bhaskar 3. Okay, let's see. So we said that one qubit can at max encode 2 values. How many values? 53. Okay, Veer. Okay, let's see. So how many elements are there? 4, 5, 6, 7, 9, 0 to 1, 2, 3, 4, 5, 6, 7 elements are there. So if you're having 7 elements, 7 divided by 2, that gives you 3.5. But we cannot have a half qubit, right? So we need one more. So we will have total of 4 qubits. So 4 qubits can represent this entire value. We have already seen that in the code implementation that I have shown you before. Okay, so now these were the easy part of the encoding methods, and these were easy to understand, easy to visualize. Next part, which we are going to discuss, is actually a tricky part, and I cannot give you simple questions like this in that section. So I won't be giving you questions in that because that will confuse you. But I'll try to explain it to you as simply as possible. So the next part. The next part uses both product and entanglement state. Now, I won't go into details of product and entanglement state, but you can understand it in this way, that if two states can be written as a multiplication, then their product state. If they cannot be written, that is an entangled state. As simple as that. Okay. Ultimately, this is the thing. But it is in more detail you need to learn. If you, ma'am will show you the process and where you need to go and what you need to do. So you will read that carefully. We'll get it there. So in this short period of time, I have only like 10 minutes left. So I'll try to finish it before that.
Take all the time in the world. We had a schedule change and someone was unable to make it right now today. So what I'm going to do is going to walk them through some of the more basics, operators and everything like that. But what you're doing, please take your time.
Okay, so we are going to understand both product and entanglement encoding. Okay, now first thing is we need to go through Z feature map. Now, what is a Z feature map? For that, I'll just take a bit of time and I'll close this and I'll open my text writer. Just wait for some time. Okay. Is my presentation stopped? Can anyone confirm? Is my presentation stopped?
No, I can still see your presentation.
Okay. Is it stopped now?
Yes,
Okay. 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 Is my screen visible? I hope it is visible.
yes. Mhm.
Okay. Now, what I told you is that we need to understand. Okay. Okay. I'll open it from here. Then it will be much better and easier. Just 1 second. Let me write it directly over here. Okay. Yeah. So let us look into it carefully. Now we need to have a very precise look into this thing. See, it has H, then it has cross N over it. And be very careful when I'm saying these things because these are important and questions from this has come because I have cleared the IBM machine learning certification and questions from here has come. So you need to understand what to look into. I cannot say the questions, that will be violation, but I'll guide you through what you need to look carefully. So H stands for Hadamard gate and N is the total number of feature parameters that you want to put. So it can be a number of qubits or how you design your circuit. Now, P we have already learned. So here I'll keep P very simple. I'll keep P here as a Z gate. Done. Nothing more than that. A simple Z gate. Or a phase gate. A phase gate. I'll take it easy. A phase gate. It is a phase gate. Okay. Now suppose my N is equal to 1. So what does it become then? It becomes 1H, 1P. End. Nothing else. So if my N is equal to 1, I'll have 1 qubit. This is my qubit. I can write it also as Q0, Q1, whatever. This is my 1 qubit. I put a H here. I put a P here. This is this one. Now, if I write it H, H, P, P, it looks very bad. So a good way of writing it is H times N into P times P. So how does that look? See, to do this thing, I need 2 qubits. So I'll have 1 qubit, I'll have another qubit, I'll put a H here, I'll put one H here, 1 P for the first, 1 P for the second, and that's done. This is your Z feature map. If you look closely, this is the same thing that we did here. In one phase gate, we put pi by 2. In another phase gate, we put pi by 3. And as simple as that. So what is my x1, xk? Remember that 1000 price of the shard, 500 price of the shard, we normalized that, converted it into an angle and put that. That one is my x1 and xk. I hope it is clear. So this is your Z feature map. It's a very popular feature map, ZFM. Remember one thing, there is no 2 qubit entangling gate. There is entanglement happening by the H only, but there is no 2 qubit entanglement happening. Here at the end, you can clearly write it as product states, but still, as it is using Hadamard, they call it that entanglement is happening somehow. Okay. Okay. Let us go to the next part. Next part is our Z feature map. So you understood clearly Z feature map used what gate? Can anyone tell what gate Z feature map used? I won't go to the previous slide. What gate it used? What gate it used? We used H and something else. What did we use? Anyone? Yeah, P. Thank you. Thank you. Yeah, Santil Kaur. Right. Yeah, Mansi Raghu, you are also right. Good job. Yeah, Bhaskar Reddy, you are also right. Good job. So, yeah. So, we used P, that is phase gate, and we used Hadamard gate. Now, as the name suggests, ZZ. So in Z feature map, we use Z gate. In ZZ feature map, we'll use ZZ gate. So this is a ZZ gate. And if you decompose the ZZ gate, using the basic gates, you find out that there is a CNOT gate, which is a 2-qubit gate. There is another CNOT gate, which is a 2-qubit gate, and a RZ gate. So this is exactly this thing after you decompose it. So what is the difference between a Z gate and a ZZ gate, and how it becomes more important to us than a simple Z gate? People say that if you use a ZZ gate, and most of the papers that you have seen which has come out before 2024 has rampantly used ZZ gate in almost all of their encodings blindedly. And why it is so important? See, so you look at this thing. So we used H, N, and P. Now, if you look at this thing, see, it has all the same thing, H, N, and P, only one thing extra, you have a UZZ. Acha, at the start of the class, we said that UZZ represents a unitary. That means this one is a unitary, right? This one is a unitary. So, we're using a unitary gate over a Z gate, as simple as that, and nothing else. But what is the beauty of it? The beauty is, it is creating actual entanglement. See, here there is no actual entanglement. You can represent it into product states. But here there is real entanglement. So you cannot change or separate out two states at this level. You cannot separate them. They're linked to each other. Okay. So that is the most beautiful thing about ZZ feature map. And in this also, if you look closely, that you can use any number of repetitions. That is, suppose you have this for one repetition, if you just copy and paste it after this thing. So if you copy and paste and have this same structure after this, then that is repetition equals to 2. If you multiply it again, repetition equals to 3. So that is repetitions. Okay. Okay. Having said that, we'll go to Pauli feature map. Now, what is Pauli feature map then? So it is similar to Z feature map or ZZ feature map. Only beautiful thing is we have some Pauli observables. As ma'am showed in the previous class, you have 4 Pauli observables, right? You have X, Y, Z, and I. You have 4 Pauli observables. And ma'am discussed in detail about those Pauli observables. We usually represent it by sigma X, sigma Y, sigma Z, and sigma I. So in ZZ feature map, we use the combination of sigma Z 2 times ZZ. That is why we tell it as ZZ feature map. In Z feature map, we use it one time. So we call it as Z feature map. In Pauli feature map, we can use any combination of it. We can use X, we can use Y, we can use Z, ZZ, XX, YY. However combination you want to make ZZZ, XYZZ, whatever. Any amount of combination you want to make, you can put. And the same circuit will run. Only thing will change is instead of U being Z or ZZ, it can be anything out of your Pauli gate. Okay, so out of your Pauli matrices. And this being very good, the problem here is it is computationally heavy. So it's nice, except the Z or ZZ are some basic combinations. Any combination that gives a good value, suppose you used one Z, then ZX, then ZZY, suppose you get a good result out of it, but it will take a lot of time to run and it's computationally heavy. On simulator also, it is very heavy. Okay. Now, I told you about these 3 important gates, and I'll just walk you through those gates very fast, because there's not much to just hold for 1 second. Yeah, can you see my screen? I hope so. Okay, so I'll walk through this code very fast. And yeah, this is your Z feature map. So what we did is that we put a header mud and then a phase gate. Is it visible? I hope so. We put a header mud and then a phase gate, another header mud, another phase gate, and then we got this. You just saw this diagram in the slide a little before. And we can also create without by doing it self. So Qiskit by itself has this Z feature map inbuilt into it. So we can use that directly, and we can call it as Z feature map, give the number of feature dimensions. It will create exactly this circuit, but it will decompose it into its own set of gates. But exactly the work will be same, the things will be same, and it has shown it by some unitaries. So this thing may look different, but this and this are exactly same. There is no difference in it. Okay. Okay, in ZZ feature map, similarly as we have Z feature map, Qiskit also has ZZ feature map. So we need to import ZZ feature map. Just pass the number of dimensions. It will make a ZZ feature. This is the thing that you just saw in the last slide also. And so this was for 2 dimensions. This is for 4 dimensions, and you get this kind of feature map. Now let us come to Pauli feature map. Suppose I have 3 dimensions. 3 dimension means 3 qubits. So see, you are you getting this thing? So to encode 3 values, I need 3 qubits. In Z feature map also, in ZZ feature map also, in Pauli feature map also, the number of values, the number of features equals to the number of qubits. So it is almost same as angle encoding or phase encoding, just a little bit more expressive and connected through the CNOT gates. So this is your Pauli feature map. Okay. Now, as I told you that you can use any Pauli, any Pauli matrices, any Paulis. So I, X, Y, X, 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 Y, any combination of it, X and ZZ, X, Y and ZZ. And then if you see all the feature names corresponding to them, so you have all of the feature names, and you can see how they look. But one thing you will find common in all of them is all of them are having a CNOT entanglement by which they are linked. So this is very important. Another thing is also there, which I didn't tell you, is this I thing. So you find S belongs to I. This is the connectivity. So if I say 0,1, this is connected. If I say 0,2, then this is connected. So this we can say as connectivity. So we can decide the connectivities also. So I walked you through basis encoding, amplitude encoding. Then we went to all the 3 types of ankle encoding. And then we went to a little bit more complex on the ankle encoding portion only, but that uses both the product and the entanglement state. We found out Z, ZZ, and Pauli encoding. Okay, this was good. But now all of them had some shortcomings. The major shortcoming was the number of states being encoded on a qubit. Now amplitude encoding was doing good. It was encoding a lot number of variables, but it was difficult to work with. So now a new and a very advanced encoding method was made from IBM. They call it as efficient SU2. Now it looks crazy. It looks crazy, and it is crazy. It looks crazy and it is crazy, but it's fantastic. Now, why it is fantastic is that see how many values it has encoded. 1, 2, 3, 4, 5, 6, 7, 8. So only 2 qubits. Just imagine the number of states that I can have in 2 qubit is 0, 0, 0, 1, 1, 0, and 1, 1. Only 4 states. But it has encoded 8 qubits, 8 values in only 4 states. And how is that possible? That's an amazing thing, right? Amazing thing. So this is done by efficient SU2. Now, after these computations, the end state that you get here, if you represent it by psi final, this one is your psi final. It's very big, it's very crazy, but it can be done. So let us see a brief look into how we can do this thing. So can you see my PPT? Yeah. Can you see my PPT? Please tell. Okay. Fine. Okay. Okay. Now can you see my PPT?
Oh, I saw it before. Go back. There you go.
Is it visible now?
Yep.
Okay.
There you go.
So what you saw in the last slide, that is in this slide, what you saw, this derivation is what you find out at the end of this slide. Now it's very small. So let us look into it. So this is the efficient SU2 diagram, right? Now we can see that we have RY gates. So 2 RY gates having 2 theta values, theta naught and theta 1. 2 phase gates. Here U1s are phase gates. See, U represents unitary. So we can represent any gate and write it as U. It is absolutely right. So 2 unitary gates. Again 2 RY gates, 2 unitary gates. So theta naught, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7. These are all the values. Now, so let us go through a little bit of basics. So we saw the RY gate. We saw the phase gate. Now, if we put phase gate on 0, we get 0. So this was the calculation. If you put phase gate on 1, we get e to the power I theta times 1. I'll share this slide if you need it. You can watch it later on. I'll just go over it because if I start telling in details, it will take a lot of time. And similarly, it goes with ry theta. So ry theta of 0 returns this state to you, and ry theta of 1 returns this state to you. Now, if we start working from the start, that is from this place, and start calculating, so u1 on ry gives you this state. Again, u1 theta 2, u1 theta 3 on ry theta 1 gives you this state. So you get from here state alpha 1, which is this one. From this line, you get alpha 2, which is the below line, right? Then what you do is you run a C naught. So you run a C naught on that state and you get a big state like this. Okay. Now in this big state, you can understand that from here it has become entangled. From here it has become entangled. So from here, if it has become entangled, then how do we proceed from here? From here, we have to proceed taking the entire state into consideration. So what we do is we apply again u and ry on it, and again u and ry on it from the top and the bottom lines. Then we get something like this. It's big, but this is what we get. And if we calculate the final state and organize it, we get this end state, which is this big, and it's right. So from the state psi, if we divide it into a bunch of classical values, a bunch of imaginary values, and we see that we can represent the state 0, 0 as a naught plus ib naught, state 1, 0 as a1 plus ib1, state 0, 1 as a2 plus ib2, and state 1, 1 as a3 plus ib3. And if we find it out that we are having 4 and 4, that is 4 DL and 4 imaginary, that is 8 distinct values encoded just into 2 qubits. And I'll be happy to say that this was the thing I corrected in IBM, and they had this wrong initially. So I flagged this and sent a request to them to correct it, and they verified it and it was corrected. And the end state that you see right now, this is what I suggested them after the calculation, and this is what you see. So it feels good to tell this thing to you also. And with all these, such a long lecture, I'm extremely sorry I took a lot of time, around 50 minutes. But yes, encoding is what it is. I can't help. And you need to study in more details, and ma'am will guide you through from here. Thanks to all of you. Thanks to all of you.
Wonderful, Siddiqui. Well done. I honestly think you did an amazing job explaining that. It would have been helpful for them if I was able to get that presentation up for the basic gates, but I think it's very different skills to be able to understand how to encode the number of qubits that you need for the data. And as most of you know, it is a representation, right, of just the numbers could be anything, right? It could be a degree, it could be the number of sales, it could be, you know, whatever it is just a way to take out what we see and translate it. And so that is a skill that, especially for your hackathons and for the big projects, it is one of the most critical skills. They might ask you here and there what kind of hardware you need if you win, and you need to be able to tell them how many qubits, calculate your error correction space. You need to be able to calculate a bunch of things. So these are very immediately applicable skills. So feel free to watch it, pause it, and I'll give, I don't know if there's any more. Oh, okay, yes. So they're asking for more coding fundamental study. Do you want to suggest something? Do you want me to show the website? What do you think, Siddiqui? Any other questions for Siddiqui?
Oh, it's fine. It's fine. You go through the course, and yeah, my LinkedIn/Shudikin. So it's as simple as that. Just go search LinkedIn/Shudikin. Send me a message. You have doubt. I'll try to explain it at my free time. I'll try my best. No need to hurry now. You go through it. Go through the course that ma'am is showing it to you and understand it properly. I just showed you a path and you need to follow that path to get the certification. It's really difficult, trust me. Getting 16 out of 20 was difficult for me. My score was 18 and it was difficult. Uh, Trust me, if you understand and do, then only you can do. ChatGPT won't give you the result. Okay, and you won't be able to clear it. So they made it in this way only. Okay. So yeah, no need to hurry. I'm there. I'm
Yeah,
always.
and then we have a couple more weeks, and what I discussed in the Discord is exactly that. If your objective here is you just want to get a participation certificate, you can. If you want to get the certificate that we provide as Qiskit advocates, organizers, EnLuz, our Entangled Cat community, then we were going to help you pass that fundamentals class, and I'm going to go over some of the fundamentals. On the live questions or the questions in Discord, ask all of the questions there. Shadiking's also a very busy man, so we have other interns that are also able to answer your questions. And so make sure you ask those questions on Discord. He's happy to connect on LinkedIn. And I'm going to share my screen over here to show you a couple of things. So we can go through this. It's going to be a little bit of information here, but I want you to see what we have. So at a high level, just a reminder for those of you listening in Spanish, we're going to have our virtual cafecito on Wednesday in the 7 p.m. EST. For those of you in English, we're going to please make sure that you vote on the general chat when we put the poll on the days that are going to be best for you for a virtual networking. So Dickon, if you have the date for IIT Ropar, let me know. Next week, we're going to have a bunch of people in person in Costa Rica and Buenos Aires in 2 weeks. So just keep that in mind. And then on the 17th, on the 20th, we're going to have it here in the Triangle. Now, to go back into the basics, want to show you here, this is the code that we use for the gate, right? So QC would be the name of assume from here on that QC is the name of your quantum circuit. And so you are going to be applying it to the qubit. We're going to have a notebook that you can follow along with this, but rather than just drop you into the pauli states and all of that, which is how this year it was suggested, we want to take you a little bit more through the basics. So again, it's slipping from state 0 to state 1. You can consider this as a 0 to 180 or to 90 degrees, depending on where you are. But this is going to be on the X gate. So for X to be 1, it is on the 0 state, and for it to be 0, it would be when it is on the other state. So just think about it as smiling or frowning. Very simplified way, but this is how you would apply it. The qubits in Qiskit are from left to right. You can think the same thing with the Z gate here. We talked about the phases, how important the negative phase is. Remember, the Hadamard gate is almost like splitting the light in two to give us that combination that allows us to put things into the different states that will allow us to perform the operations that are important for us. So if, for example, you're trying to reach entanglement or superposition, make sure that you know which gates to use. In the case of the Z gate, you think about a switch in the phase, and that is represented as that -1. And so keep that in mind. Again, the gate is just .Z and the qubit that you're going to apply it with. QC could be the name of your quantum circuit, right? This Hadamard gate that we're talking about, it's to be thought as, a 50-50, right? And as you see here, here's a perfect example where for the code, instead of QC, they called it circuit. And this is the name that they gave to their quantum circuit. And this is a 1 qubit circuit. And so we're applying this to qubit 0. Again, it starts from 0 to right, and then we're measuring it in 0. With what we're doing here, it says that there is a 50-50 chance, and this is what the importance is of this Hadamard gate. We could go into a lot of detail about that, but what it is is kind of, creating that state where you can part from the rest of the combinations that are critical to quantum. Now, the Hadamard matrix representation here is for this zero ket. Here is this representation. The way I think of it is that if there is a zero here, similar to how Raynell explained it from IBM, to consider this as the x-axis, and then, 1 here. Now, if you could see here in the Hadamard gate, you have the negative phase here, and it is in these matrices, whenever you see 1 over the square root of 2, this is a consideration of the 50-50. So when we are measuring amplitudes and you have 2 different ones, if you, like Raynell explained, by having this in front of the ket, then we're saying you got a 50-50 chance. You might have 25 to 0.75, depending on what you have as the in front of your ket state. But just remember that this is a key point here. And then there are times where this is something that you need to achieve through a combination of different things. So just very important representation to keep in mind. Now, we talked about, so you can talk about the qubit unitary operations. Pauli operations are definitely one of them. Again, these are like 1 qubit operations. You have the unitary one here. You have the ones that you can achieve with a pauli X, pauli Y, pauli Z. Again, the combinations with anything that has to do with I is called identity. And so it doesn't really affect it. So keep that in mind. We could see here the effects, and then I'll get on the Z, you can see the negative phase flip. Now, in terms of the Qiskit libraries and utility patterns, we're trying to take you through steps similar to what Raynell described, and this is just a reiteration of a lot of that in a different way. We want to map the circuits that we import into different ones. So for this one, we use the sparse Pauli operators. And if we were going to optimize the circuit, we would use a transpiler to translate the gates that we have into what the hardware has, similar to how he explained it. And so we have some examples where you can execute this in an AI simulator, and then you can post-process the results using Python or using Qiskit for the visualizations. Now, I want to take you through something that Sudikin had talked about, and it has to do with optimization, minimums, and energy of a state. In an ideal world, well, some of these algorithms are trying to find the minimum. What's the path where you can get to the lowest state? This is what we would consider the ideal path, the absolute minimum. However, sometimes our algorithms might end up here, might end up here, might end up somewhere over here. And then that doesn't always mean that we have the minimum. This is important, the absolute minimum, but we are looking for minimums and optimization routes to get to, for example, the in finance, the lowest loss, right, of money, managing risk and other things. Also for logistics, the lowest cost, the shortest distance. You have the traveling salesman and all of the examples that most people use when they're teaching this sort of subject. And so when we talk about energy state, sorry for the typo there, we end up looking, this is what we do for some of the drug discovery or material science. So there is something called potentially functional theory that brings you to, well, what is that the minimum energy state, so we can bring some elements together, and depending on the combination of all of that, is it going to be stable? Is it not going to be a stable material? And similar with some of the other quantum chemistry aspects, you'll find that understanding when to find the minimum of an energy state is very important. Now, just keep in mind, not every algorithm guarantees the lowest energy state of the system, but that is what we're always technically looking for. There are some algorithms here. The QAOA algorithm is an algorithm that would be, let me delete this. Yep. That would be optimal for some types of optimizations in finance, and I've seen it used in a couple of other use cases that I can't think of at this moment. But it's really important for you to know that what they're trying to do is just using a series of gates, right, to find that optimal solution. What would be the shortest path, the lowest loss, all of that. For quantum and others, which we will not be necessarily looking into in depth, except for an example on the last week of our series on how it applies to security, you can use this, you can get to this, but it has to be a QAOA type of equation. This is really critical because they need to be quadratic equations. And so it's a whole different topic that we may not get to in detail, but I can share some recordings on it so you can understand the criticality of having the dynamics of your system translated into an equation that makes sense and captures as much as you can the dynamics of your system. But again, this one is trying to find the ground state of an Ising model. And so here you have Ising Hamiltonians that it is looking for the minimum energy state. We're going to just say the minimum for that system or for that algorithm, the best that it could do. There is no guarantee that it is an absolute minimum. So why do we do it again? Traffic, logistics, finance, healthcare, and other things. And just keep in mind that the more complex, as heavier discussed, a problem is, and the more dynamics that you're going to have in your formula. If something goes in, we did something with climate change a couple of years ago, and the chaos model has so many variables that representation in a formula itself was very complex. And so computational need for that isn't just incredibly big. What you need to know is that it is very important, as we talked about in our first lesson, to understand how you're really translating the situation in the real world to your data set. Do you understand what is affecting it across time, across seasons, and different things? For example, even logistics and finance, right? If your equation or the representation of your data doesn't take into effect seasonal issues, for example, for a place that has 4 seasons like Chicago, where I grew up, then you wouldn't consider the delays of snow and things like that, so it would not be very accurate. So you could do initial preliminary strategies with classical, add a time series representation, then do a hybrid one with quantum, complement them, think about ensemble models, things that will feed different portions to it. One of my favorite strategic books, or I guess methodologies, has to do with systems engineering and how either defense or the space missions design. So you have to do modular design, create redundancy of systems, and make sure that you encapsulate it in the minimum most critical part. If you think about designing your algorithms and architectures similarly, then you're not looking for one algorithm to solve it all. You are looking for one algorithm to solve this part, another one this part, another one this part. And then you are creating a pipeline of things that are operating in the best way. If in a world where we had the extreme computational ability right now to do quantum and encapsulate all the variables and classical without any limitations of cost or performance, it would be great to do, a one cohesive model that does everything. But one of the best practices in my experience is to consider smaller models that can showcase different sections of data and bring them all together. So just a recommendation based on some experience there. This way, as things progress, then you can just update that particular model. Now, belt states are super important in what we are teaching, and there will be some information that you can read to kind of understand what exactly we're trying to get to. But here, I'm sharing this mostly to show you what a Hadamard gate looks like, the C knot, which is going to create a superposition and entanglement between all of these. And then, as you can see here, the measurement that takes place is applying not only a Z gate to this qubit 0, but then we have two measurements of qubit 0 and qubit 1. This combination is critical for you to be able to execute a certain type of algorithms and steps in the next more advanced, like dosha and different things. We will have what you'll see on Wednesday is that some of them just say there's something called an oracle, and you'll be able to say, hey, you know what, this one's consistent, this one flips, and then one is always 0, one is always 1. The only reason we're going to go through that is so you know that an oracle is for you to consider a black box. Some people get really stuck with the oracles, and what I want you to know at a practical level is that if you are not trying to make a better oracle, it's a box that will be defined as one or the other, and that is what you need to know so you know how to use it, just like we are teaching you how to use the Hadamard gate, how to know what it does within your circuit, right? Changes the phase, flips the bit, these are dependent now, and then the Hadamard creates a state. So you'll find a trend of either Hadamard C knots or X gates and Z gates. This is a very, very popular combination. Then when we want to look for the sampler run, you can look at this is why we had the shots example up there. It's telling me out of 1,000, out of 10,000 shots, give me the probability. This is why we call it a probabilistic model, not a deterministic in quantum. Tell me the probabilities that this is going to be either 1, 0, 1 or 1, 0, or that, in the qubit, that it's going to be that it's going to be 1 in either of these states. And so you can see how it switches, right? Remember, we had 2 qubits, right? And so which combination am I going to get? Now, as Raynell explained, when we get to this point, we want them to be, this is a perfect example of one of the critical states that we're looking to achieve, which is them to be in 0, 1, and 1, 0. I'm going to send the presentation so you can study that with a little bit more time. And so here is some of the Qiskit primitives. I'm going to walk you through it in a different way, but I really wanted you to have a chance to look at some of these basics, to see it in a way that that gave you a bit of a different perspective. And there is so much that you can learn here, but I'm going to show you one of our objective for the intermediate level learner in our course is this is the quantum machine learning class. And so they explain things here. They do encodings, quantum kernels. And so Sujikin is very gracefully taking you through his version of how to explain this better, or in a way that is more understandable for most of us. This is a great tool, great representations, all of that, but it isn't always as simplified. And so you can see that they take you through the phi operators. What did I tell you here? This means that, we are in superposition. And so again, the combinations, right? If you see this, you might guess that there's Hadamard gate there. And then we have a couple of, this is what, he was walking you through, but you can compare how simple this is and just the robustness of what he gave you. And then also one of the things I want to show you here is that there are other courses that you can take to expand your knowledge. Now, we have very intentionally decided not to take you through this sort of information in the same way because it gets to a point where it might be a little mathematically heavy. But for those, and since we have some people that are in high school, we're giving them different support. Here is how, the heads and tails is explained. Again, 50% chance. And so, if heads is here and tails is there, what I recommend is that if you have time, go through it. They start explaining deterministic operations in this kind of way, which not everyone has learned that way. And then they compare it to the quantum side. If this is how you learn easiest, please go for it. And then here they will explain the quantum state vectors. They will take you through all of this. And now it changes from half probability to 1 over the square root of 2, and so on and so on. And so they start showing you that there is always, that's always going to be the sum of 1, no matter what probabilities are. This is probably the 5th or 6th time that you've heard that, but it's really important that you understand it. And so when we are able to represent this, sometimes you'll see in the plus state or the minus state. And what does that mean? Is that here is that negative phase. And so it's a different way to visualize it, right? So you have the Qiskit implementation, and here you'll get through a different way. For some people, it's a good way to learn it. For some people, they got really lost. So we just wanted to offer you an alternative way. What we just kind of observed here is in the quantum information. I'm going to take you through some of the, I'm sorry for the scrolling here, but they do it with a card of decks. Not always easiest to understand if you're not so good on the visuals, but gonna go over here to see if we can get to the pauli states. Nope. Here we go. Here are the pauli states. So inner products and circuits. So if you don't have a background in Boolean circuits, this might not be the easiest for you to understand, but if you do and you have a background in electronics, by all means, go through it and say, got it, right? If you have a background mathematics and this is way easier for you, then please do. Just know that we are going to be basing our quizzes on more practical things, and it's not going to be more chat GPT, but everything that we've discussed. So and here they talk about the entanglement, which is what I was talking about. Next week we're going to go through quantum teleportation, the typical Alex and Bob example, and we're going to do it with a little bit of humor here. So this is the CHS inequality, and so we'll be able to see what that looks like. Just want to show you that the basics of quantum information is a little bit different than the fundamentals on algorithms. This one starts taking you through more of the fundamentals that we're going to see later. So this Dosh algorithm and this Dosh-Josa algorithm that I was telling you about with this unitary function, that is what we're going to be prepared to explain to you on Wednesday at a really high level, Simon's algorithm, and then just by what you have heard at a more advanced level, what phase estimation is. We may not go through Shor's algorithm because it might not be where our time is needed, but Grover's algorithm is something, is for unstructured search. So if you want to go deeper into this, by all means, and if you want to work towards this this certification, please do so. This is directly with IBM. We do not, we won't be giving certifications with that, but the notebook that we have here does talk about the pauli operators, the superposition and the block sphere rotations that we were just talking with this probability. And so you could see it's explained a little bit different. So we will be walking through it a little bit more on Wednesday. So a lot of information, but the objective here is to give you different ways to learn it and to also allow for you to ask questions. And Okay, I see Michael Ndai sent me a question. Oh yeah, I was wondering what had happened here. Okay, I'm gonna just look over here to see if we have questions we can answer. All right. So just please make sure that you have everything in the Discord and that you are watching for the polls and the next virtual office hours and all of the above. So if there are no specific questions, I'm going to wrap up our event at this time. Thank you for your attention.